Reasoning without the right context is just expensive hallucination. Wow, that quote from a recent supermemory research article just absolutely hits the nail on the head, doesn't it? You can have the most advanced large language model on the planet, capable of mind-blowing reasoning. But if you just drop it into production without the right context, yeah, it's just gonna fail. And really, that brings us right to the single biggest challenge in modern AI. We've basically mastered the reasoning engine, right? But we're still kind of fumbling around in the dark figuring out the hard drive. So how do we actually build agents that remember? How do we give them that crucial context they need to stop hallucinating and actually start working autonomously? Well, welcome to today's Explainer. We're diving straight into Module 2, the bridge to agentic workflows. We're going to explore exactly how we take these large language models, leverage things like transformers and tokenization, and make them truly stateful. To really grasp why memory is so absolutely crucial, we've got to look at two fundamentally different paradigms here. First, think about traditional automation. It runs on fixed, predictable, manual rules. If X happens, do Y. And hey, it works perfectly until it hits a weird edge case. Agentic workflows, on the other hand, they are built for variable, messy, multi-step environments where real human-like judgment that's been honed through RLHF, by the way, is genuinely required. An agent doesn't just blindly follow a script. It reasons its way through a problem. And to do that over multiple steps, or even over multiple days, it absolutely must have persistent memory. So here is our roadmap for today. We're going to cover why basic memory fails, look at the 4 biological memory types, check out the technical bridge of tokenization and function calling, structure some knowledge with graphs, and finally get into active dreaming. Let's get to it. Okay, kicking things off with Section 1, Basic Memory Fails and the Limits of Flat Storage. Early on, a lot of developers thought, hey, we can just solve memory by dumping all the data into a basic, flat vector database. But as recent research clearly shows, that breaks down terribly at scale. In fact, it leads to 4 catastrophic failures. First up, context poisoning. If an agent hallucinates a mistake, it literally stores that error, pulls it up later, and just reinforces its own bad guess. Not great. Second is context distraction. Because flat databases rely on broad mathematical embeddings, a vector search often spits out semantic matches that are completely irrelevant to the actual task, totally distracting the agent. Third, we get context clash. This is where the database loads straight-up contradictory facts into the context window, like, say, a user's old address alongside their new one, leaving the model to just guess which one is right. And finally, work duplication. Multi-agent systems basically end up doing the exact same work over and over again because they don't have a shared coherent memory state. Moving on to Section 2, 4 types of memory and the biological metaphor. To fix these massive failures, developers are actually looking inward. They're mapping agentic memory directly to human cognitive biology. And it starts with working memory. Think of this as the AI's RAM. It maps directly to the transformer model's active context window. Because the self-attention mechanism requires massive compute power, this space is incredibly fast but strictly temporary. It holds your current conversation, recent tool outputs, and whatever variables are needed right this second. But the catch? Once you hit that token limit, bam, it resets. Next up, we have episodic memory. This stores specific past experiences. It tracks exactly what happened. This is the crucial layer that lets an agent maintain a sense of continuity across multiple sessions. It's literally the reason an AI can understand that, oh, the user I'm talking to right now is the exact same person I helped yesterday, because it recalls that temporal sequence of interactions. Then there's semantic memory. Now, unlike episodic memory, which tracks personal, specific experiences, semantic memory tracks what is true. This is the agent's foundational, persistent knowledge base. It holds verifiable facts about the world, or whatever specific domain the agent is working in, and it's constantly being updated from external sources. And finally, we have procedural memory. This right here is the true automation engine. It encodes learned skills and action sequences. So instead of having to figure out from scratch how to authenticate an API or run a test every single time, the agent just retrieves these validated procedures, which are usually stored as highly structured outputs like pydantic schemas. It's a huge time saver. All right, Section 3, tokenization and function calling. This is where we cross the technical bridge. Understanding the whole biological metaphor is great, but how does that actually work in software? Well, look at this. What's really fascinating about specialized, tokenized memory frameworks like Hippocampus is their sheer speed. Because LLMs natively operate on integer sequences called token IDs, this framework completely skips the heavy cost of repeated tokenization. Instead, it uses a dual representation strategy to create a highly compressed signature matrix. As you can see from the search times here, this lets the system search directly inside that compressed domain ridiculously fast, keeping things snappy even during really long, complex agentic workflows. So let's look at how this builds into an actual query pipeline. A query comes in, and the LLM extracts the keywords. Boom, those are instantly converted into a binary token signature. The system then runs a lightning-fast approximate search on a signature dynamic wavelet matrix. Got a match? Great. It uses those indices to reconstruct the exact, full-resolution content from a parallel content matrix. It is a completely lossless exact reconstruction, and it totally bypasses the insane computational cost of standard vector similarity scans. But hey, retrieving memory is really only half the battle. The agent also has to manage it, and this is where function calling really becomes the bridge to true autonomy. Frameworks like MemGPT basically treat the LLM like an operating system. The agent is trained to use explicit function calls, things like load_context, update_core memory, or archive_memory, to actively curate its own working memory. By deciding what stays in the active window and what gets kicked out to long-term storage, the agent drastically cuts down on token costs and avoids context window overflow. It's super smart. Which brings us perfectly to Section 4, Hierarchical and Graph Systems for Structuring Knowledge. So the agent is actively curating its memory, right? But what happens when that long-term storage scales up to, say, millions of entries? Without structure, the agent would just drown in its own knowledge. To prevent that awful context distraction we talked about earlier, we use hierarchical memory, or HMEM. Instead of doing a lazy, broad semantic search across everything, HMEM organizes information into routing layers: domain, category, memory trace, and then finally the specific episode. It's kind of like reading the label on a filing cabinet drawer before you blindly start rummaging through the folders. By filtering out irrelevant branches early on using self-position index encoding, the agent zeroes in on exactly what it needs. No more getting distracted by random semantic noise. But sometimes, honestly, even hierarchical vector search just isn't enough, especially when facts have to be exact. Semantic similarity is inherently fuzzy, and if an agent is acting as, let's say, a medical assistant, fuzzy is simply not acceptable. It needs to know for sure if two drugs have a lethal interaction. That's where GraphRag comes in. Knowledge graphs store information as explicit nodes and edges, which enables multi-hop reasoning. The agent can literally trace a concrete path from patient to condition to drug to interaction. It provides an explainable, completely verifiable chain of logic that simple vector similarity fundamentally cannot do. And finally, Section 5, Active Dreaming and Continuous Consolidation. Let's see how agents actually learn. Okay, so we've covered storage and retrieval, but how do agents improve over time? Well, just like humans consolidate memories during our sleep phase, advanced AI agents use an offline period to learn. Instead of treating every single interaction independently, the system takes raw episodic memory traces, clusters them together, and abstracts them into verified semantic rules. Here is how that consolidation actually plays out, and this is super cool. First, a reflector analyzes past failures. Second, an abstractor comes up with a candidate rule to prevent that failure from ever happening again. Third, and this is the absolute magic part, a dreamer simulates synthetic, counterfactual scenarios just to test this new rule against edge cases. And finally, a verifier tests it. This whole process is brilliant because it prevents the agent from overgeneralizing a solution or suffering from catastrophic forgetting when it's learning new tasks. But a big part of learning is also knowing what to just throw away. Unbounded memory sounds great, but it's actually a massive liability. It inflates your storage costs and dilutes retrieval quality, so agents must strategically forget. They use a selective forgetting algorithm that relies on a recency, relevance, frequency formula. Basically, if a piece of data hasn't been accessed recently, isn't really relevant to current tasks, and has a low overall frequency of use, it gets pruned. Simple as that. Memory has to be treated as a highly curated strategic resource.
Which honestly leaves us with a pretty profound realization here. We are moving so far beyond simple chatbots that just read from a flat database. If an AI agent can actively manage its own context window, use multi-hop reasoning for precise facts, actively dream offline to simulate counterfactuals, and literally update its own operating rules based on past mistakes, is it really just a software tool? Or are you looking at the underlying architecture of your newest colleague? Definitely something to chew on as you design your next workflow. Thanks so much for joining me on this explainer, and keep learning.